Hey, what's going on, everybody? Happy Saturday. And in today's video, we are actually going to do some physics. I am going to summarize one-dimensional motion in hopefully what is a quick video where I kind of run through all the terms, give the mathematical definition of each term, do a little interactive game I have to showcase each of the terms, to demonstrate them, to display them, and then we'll wrap it up. And so, one-dimensional motion is motion along one dimension, and you can think of an XY coordinate plane, and the x-axis is one dimension, and so you can move left or right. Alternatively, you could move along the y-axis, which would just be up or down. And if you notice, and of course you could have the z-axis as well, but that's for 3 dimensions. But in our case, we're only concerned with 1 dimension, and for most of these examples, we'll use the x-axis. And so if you think about it, you can't be turning or changing directions other than going left or right. Otherwise, you'd be moving along another dimension. So all of our examples are 1 dimension. And so the first term that we care about is called displacement. And so displacement, using English language, is the change in position of an object, or the end point for an object, the difference between the end point and the starting point of an object. And we can represent this with a mathematical definition such that the x position the final x position, minus the initial x position. And this is displacement. And so if you think about it, I'll bring us to this little interactive where I have this guy here. We could say his initial position is right here, and if I move him over here, this is his final position. And so the distance between this position and his initial position is the displacement from here to here. And it's important to recognize that displacement is different than the distance traveled. And so imagine we had a path we took. It went just like something like this. And so this is the final point, and this is the initial starting point. The displacement is not this entire trajectory measured. It's just from here to here. This is our displacement right here. And mathematically, it's really just whatever. If we're measuring in meters, it would be this position in meters minus this position in meters. And so that would be our displacement. If we measure this entire route we took to get to this final position, that would be called the distance. The distance traveled, and we can say in meters, for example. This is also in meters. And so where does displacement come in handy? Displacement comes in handy when we think about average velocity, our next term. And what is average velocity? Average velocity is our displacement divided by our change in time. So how long we move from our final position from our initial position. And so you would plug in x final minus x initial in the numerator, and final time minus the initial time. And so we could go back to our interactive buddy, and we could say that I moved him just like this for 4 seconds, and then he stops. Okay. We would calculate where he started, which he started over here, And this is his final spot over here. I didn't mean to touch him again. Whoops. Over here, the difference between this ending position and his initial position divided by the time I was moving him, which was about 4 seconds. And so that would be his average velocity. Average velocity. And when you think about average velocity, sometimes it'll just remove the average and say velocity. So displacement over time. And the next term to consider would be the instantaneous velocity. And also for this interactive guy, remember, we can consider him to be standing on an x-axis, and so he's only moving right or left. I'm not moving him up or down. We're not measuring any other dimension, just this x dimension, left and right. Okay. So instantaneous, if I could spell instantaneous, let's fix that. Instantaneous velocity. So instead of taking the change in time, we want to know the instantaneous velocity, which is the limit. So we're going to do some calculus in here. The limit as t, the interval, the change in t, approaches 0 for displacement. And by the way, I'm going to represent displacement now. I'm going to represent displacement as change in x over change in t, which is time. And so we are taking the limit as t approaches 0, so as the interval, the time interval, gets closer and closer to 0. And really this is just the derivative. The derivative of x dt. So dx dt. And so the instantaneous velocity is the derivative of a change in x over change in t graph. And so we can find the instantaneous velocity at any point in time we desire by using the limit as t approaches 0 for that given point in time. And then the next term we could consider is speed. And speed is actually different than velocity. Speed cares only about the magnitude of the object's motion, whereas velocity cares about its direction and magnitude. So displacement, in another way to think about it, displacement can be positive or negative. It can be positive or negative. However, speed is distance. The distance traveled over the change in time. This would be average speed. And so distance is always positive. You can't have a negative distance traveled. You can measure this and it will be a positive number every time you move from one distance to another. Whereas displacement can be negative. We can move along the negative direction, which would imply, based on the context, whatever the context is, that we are moving left instead of right, because we have given you the contextual information to say that anything that's positive is right, anything that's negative is moving left. But with distance, it's always positive. So the average speed, even if we change directions, so if I go back to our interactive, so even if I'm going in this direction or this direction, the speed in both those directions is exactly the same. Whereas this velocity would be negative in this direction, the velocity in this direction would be positive. Negative, positive velocity, positive speed, positive speed. And so that's the difference between those two, in addition to the distance traveled, rather than the displacement. The displacement here would be a lot less than the speed, because the distance traveled would be greater, but the time would also be greater. All right. And just like instantaneous velocity, we have instantaneous speed, which again is just the derivative. Instantaneous speed, which is just the derivative of our change in x over the derivative of t, which, as we recall, is the limit as t approaches 0. And so here's the quick summary of one-dimensional motion and the important terms. And we can actually continue these terms. I almost forgot. Average acceleration. And I also want to throw in units for those, but I'll do that at the end. So average acceleration is going to be change in velocity over change in the time to travel that velocity. And so we can think about this as our change in motion along a particular interval of time. So if we say for 4 seconds, I am moving this guy around. So he probably moved quicker there than he did here. Probably moved quicker right there than he did there. And so we could take this change in velocity, so the final velocity versus the initial velocity, divided by the time, and we will get our average acceleration. So just like that. But perhaps we wanted to know the instantaneous velocity, or the instantaneous acceleration right there. What we could do is find the derivative. The instantaneous... Wow, I don't know why I don't want to write all of it out. Instantaneous acceleration. This is going to be the limit as t approaches 0 of the change in v over the change in t. Again, which we could represent as dv dt, or the derivative. So a little bit of calculus once again. And so there we have all of the major terms you'll use in motion in one direction. I'll also go over kinematic formulas. So there are actually about 4 formulas that have been derived for an object that has constant acceleration. And constant acceleration doesn't occur very frequently in nature, but it does in engineering, human engineering systems. And so if you are trying to become an engineer, perhaps knowing these kinematic formulas would be very valuable. They are only used when acceleration is constant. So if we take our interactive buddy here, an object that has constant acceleration could be traveling the same pace, which means the acceleration is 0, as long as they're moving the exact same pace and in the same direction. That at that point acceleration is 0. Or alternatively, we can move in the same direction and consistently get faster and faster at the same rate. So he's getting faster and faster and faster at the same rate and then stops, okay? Or alternatively, he'd go going fast and slowing down at the same rate. Whoops. We could be going fast and then slowing down the same rate, as long as we're going in the same direction. And so that's when acceleration is constant. I'll let you look up the kinematic formulas on your own. And then the last final term, final concept we'll go over is free-falling bodies. But before I do that, so that basically this is motion still in one direction or one dimension, but we're going to think about it from the y-axis. Free-falling bodies, free falls, an object free-falling is concerned with the y-axis. But before I do that, let's look at some of these terms that we just described mathematically and think about their units. So displacement is going to be, you can think about meters, right? Your position initially was 4 meters. Your final position was 10 meters. So 10 minus 4, you have a displacement of 6 meters. However, for average velocity, we have meters over seconds. And so that's where you see the commonly referred to meters per second. You're traveling however meters over an interval of time, and that is seconds. So you can do a little bit of arithmetic and get meters. You can get the reduced amount of meters per second. The simplified, I should say, not reduced, the simplified meters per second amount. And then instantaneous velocity would be meters per second as well, right? Position, change in position over change in time, meters per second. Average velocity would be, or average speed, it's also meters per second, but can never go negative. Instantaneous speed, meters per second. Average velocity, however, will be different. We have our velocity in the numerator, so meters per second, divided by second, so that equals our meters per second squared. Another way to think about this is imagine meters per second drawn like this over second. We can bring our second up here. And so we multiply meters per second times 1 over second, because you multiply by the reciprocal. M times 1 is just M. S times S is S squared. Another way we could even go further. We could say, like, imagine this is 5/12, and you could times it by 1 over 12. What do we get? We get 5 over 144 if they were integers instead of letters. And so that's an explanation for meters per second squared and how we get average acceleration in that sense. And instantaneous acceleration would also be meters per second squared. And so quickly before I wrap up this video, there is actually one example of constant acceleration that arises in nature. And this is called free falling, or the acceleration due to gravity near the Earth's surface. So the acceleration due to gravity near the Earth's surface has been measured to be roughly 9.8 meters per second squared. And this is a constant, a universal constant, near the Earth's surface specifically. So the acceleration due to gravity on Mars or on the moon or near the sun would be much different than it is here. But we live near the Earth's surface, so that's where it's most useful, although we potentially will be living on Mars at some point, and so it might be useful to know that acceleration due to gravity. And so if we go over to our interactive buddy, so you guys don't want to see that, we can demonstrate the acceleration due to gravity. So if I bring this guy up here and I drop him, he will accelerate downwards. Obviously this isn't precise or even accurate. He's not falling, doesn't even look like he's actually accelerating downward. It looks like he's falling at a constant rate. So let's imagine he's in free fall already at this point. He is traveling downward in free fall right there. And we can use kinematic formulas that I had you look up to identify his velocity at this point or this point. Or maybe we want to know his position after a certain amount of time. We could use kinematic formulas and the gravitational constant little g, or 9.8 meters per second squared. And so that's free falling in a nutshell, and that's one-dimensional motion in a nutshell. And so I think this is a good primer for your initial studies in calc-based physics. And so with that, I'll leave you guys, and I'll see you in the next video.